Okay. If you had your notes, it would look something like this. Okay. So we've already talked about some of this stuff. We've gotten a running start at actually balancing equations using this method I'm going to show you. The only way this method works is if you're dealing with a redox reaction. So a redox reaction means that something's oxidized and something's reduced on either side of the reaction arrow. So let's see. We're going to be dealing with solutions that, now not all redox reactions are an aqueous solution, but that's what we're going to be dealing with today. Oftentimes we just write the net ionic equation. That means what spectators are removed. So that's kind of we're going to see that approach. The other thing is we're used to balancing by inspection, making sure we have the atoms of each type of element, the same number on either side of the reaction arrow. Well, now we're going to balance them not by inspection, but ultimately when they're balanced, they will be balanced for mass. Okay, so again, you'll have the same number of atoms of each type of element on either side of the arrow, but they'll also be balanced for charge. So that's something kind of new. So the half reaction actually involves separating your reaction of interest into two different reactions. And one reaction will represent oxidation and one reaction will represent reduction. Okay, so there's that. Now we talked, at some point you're going to want to get this through your head, how this all works. Oxidation occurs at the anode. Oxidation means that the number is increasing its oxidation number. As it increases in oxidation number, it basically releases electrons. That's how I think of it. So a reduction occurs at the cathode, and it's the taking in of electrons, and you're going to see its oxidation number decrease on the product side. So we're going to work with each half reaction separately until we get them just how we want, and then we're going to add them together at the end. So it's fun. Remember that I said that your final exam is going to have some of this Unit 5 stuff. So does it make sense that the fact that I'm taking like 2 hours out of my day to talk about it, might I put it on a final exam? I just might. Okay, so there's your blatant hint. So we're going to do it in two parts. One's under acidic conditions, one under basic conditions. So starting with the acidic conditions. Acidic, I guess, means that you have extra protons, H pluses. Okay, so we're going to be able to actually pull from this is different by balancing by inspection. Ultimately, you're going to be adding stuff to your equation along the way. H pluses and OH and H2Os. We're also in this process, you're going to see, we're going to actually track those electrons that are given up during oxidation and absorbed during reduction. So that's kind of fun. So here are the steps. And actually, you hopefully have your lab manual and kind of both side by side. Your lab manual kind of sets these steps, kind of hits you over the head with these steps. So first step, and we're going to do, like I said, an example, and then I'm going to turn you loose with two examples. One, let's see how fast you guys are at them. Okay, first off, we're going to break them. First, to me, 1A, and this is 1. 1A, what I would do is go along the thing I want to balance, and I would write little oxidation numbers over everything. That's what I would do. And then you're going to basically separate them out into two half reactions. And you can already kind of see maybe the worksheets, if you kind of go ahead, that you're going to have one column is going to be one half reaction, one column is going to be another half reaction, and at the end you're going to add the two columns, basically. Okay. Now you don't necessarily need to know which half reaction is oxidation, which half reaction is reduction. It will become apparent as you go through this process, though. Okay. Oops. Forgot to turn off my thingy. I might need a hotel. Yeah, so this is just kind of consistent. We said that with the oxidation, you're going to see electrons given up, and with the reduction, you're going to see electrons consumed. That's step 1. Step 2 then is going to feel kind of strange. You're actually going to introduce, step number 2 won't feel strange. Step number 2 is basically what you have done before. You're going to balance by inspection, putting a stoichiometric coefficient in front of where you need to, to balance for everything except hydrogen and oxygen. Leave hydrogen and oxygen alone. Step number 3 is to go ahead and balance your oxygen. So if you have oxygen, sometimes it'll be not applicable. If you have oxygen and need to balance it, you're going to introduce H2O wherever you need to, on whichever side needs to be there. Notice that you don't balance your oxygen by simply adding just raw oxygen atoms, nor do you add molecular oxygen O2 molecules. Step number 4 on our kind of chain of things we're going to do to both half reactions. Step number 4 is to go ahead and, when I say fix our hydrogens. The problem with step number 3 was you introduced oxygen by adding H2O. Well, you introduced extra hydrogen. So now you're going to fix that on the other side by adding H pluses, because remember, this is an acidic solution. Notice that you can't fix the hydrogen by just adding this regular H's, nor can you fix the hydrogen by adding molecular hydrogen, H2 gas. It's H pluses. It's in acidic conditions. Step number 5 down here somewhere. Now we're ready to go ahead and balance it for charge. Again, we look at each half reaction by itself. And we're going to see on either side of the reaction arrow, you're going to see that you might have its extra plus over here. And anyway, I'll show you what I mean by that. We balance it for charge on either side of the reaction arrow for both half reactions by adding electrons. Because remember, these are redox reactions. Electrons are going to be given up, electrons are going to be taken in. Oh, this says, note that when you balance it, it doesn't mean that you're going to have 0 charge and 0 charge. You could have a +1 charge over here and a +1 charge over here. Okay. Step number 6 is to look then finally at both half reactions and say, hey, I have 6 electrons that are given up over here in oxidation, but I have only 3 electrons that are consumed over here in reduction. Well, if you have 6 and 3, what we're going to do in that case is basically scale up the half reaction over here, the second one, so that it consumes 6 electrons. So we're going to do that by changing the stoichiometric coefficients. It's easier to show you, but these are honestly, I promise you, the steps that we'll be doing. Step number 7, we're getting close. By step number 6, basically, you have the same number of electrons given up and the same number of electrons taken in. That's awesome. Step number 7 is your Hail Mary, where you're just basically going to add those 2 half reactions. Now, when you add them, you know that your electrons are going to cancel because you made it that way in step 6. Okay. Step number 7 is kind of your cleanup. You go ahead and let terms cancel like we did before when we added equations or equilibria, and combine terms and let them cancel, that sort of thing. Step number 8 is to double check. And the things you're going to double check are that you have the same numbers of each type of atom on either side of the reaction arrow. And the other thing is it's balanced for charge. Okay. Whew. So let's do an example. I'm not sure, Quade, check in yours. You might have this example now. Do you have this example? Okay. So this is, oh good, it's nice and big in the lab. So you might want to switch Mike to your lab then. So the first thing I'm going to do, and I call it step 1A, is I'm actually going to go, and let's go around the room. That was so fun yesterday. I'm going to pick on chromium, oxygen, iodine, and then chromium and iodine, and I want oxidation numbers for each of those. So I'm going to write them over the top. I say this step is optional, but I don't know. I think it should be done. So Mike, I'm going to pick on you first. So this oxygen right here on the reactant side, what is the oxidation number for oxygen? So were you here? -2. You were here. Very good, -2. So Quade, I'm going to pick on you, and I'm not going to write my funky little math thing with the question mark. That's a -2. So we got -2 times 7, -14. So he's saying 6 for the chromiums. I'm liking it. And I see you got a shake of the nod here, the head there. Very good. +6. Right? You buy that, Mike? I do. Quade?
So since there's 7 -2, it's -14, but total has -2 charge. So also charges.
Perfect. Yay. So Olivia, what is that I minus 1? What is its oxidation number? It is just a -1. Perfect. Okay, back to you, Mike. So the chromium +3, what's its oxidation number? It is a +3. You get my favorite equation, so this is +3. And actually, we talked about it. We have 3 I's collectively with a -1 charge. So what is each one of their oxidation states? -1/3. I'm liking it. So Olivia, what is being oxidized? It's a weird one.
It's CO2. For oxide, it's lowering or
Increase.
okay.
And it's just going to be an atom. You can't read this. This is a -2 to -2. Oh, sorry, there's no more O there. So your choices are chromium and I. So the I goes from the, so what do you think? It is just the I. I know it's weird, but if you think of continuum, I'm bad with negative numbers. But I think of 0 over here, and this is my -1, and my -1/3 is here. Did I do that right, or do we usually do negative numbers over here? Okay, negative numbers over here.
Okay, yeah.
There, -1, thank you. -1/3, 0. Yeah. So it's being oxidized. See why I'm not a math teacher. Okay. Very good. So we got chromium, or excuse me, iodine going from -1 to a -1/3. That's oxidation. And again, you wouldn't have to know that, but I think it's I kind of think it's got a good exercise. So Mike, what is being reduced? And it'd be an atom. What's going down in oxidation number? Chromium. Yep. Very good. Reduced. Excellent. Okay. So I think that's helpful because now we need 2 half reactions. And our 2 half reactions are going to deal with the things we just identified. I think we usually go with oxidation on the left and reduction on the right. So we end up with something like this. Oh, do I have reduction? I guess I have reduction on the left. Okay, we'll get reduction on the left, oxidation on the right. Okay. So do you see where you can tease those 2 half reactions out of that? We took the thing that was being oxidized, or what did I say, reduced, things being reduced, chromium. So we took the whole Cr2O7 2- because it has the chromium +6 oxidation state, and we put chromium +3 on the other side. Okay, so the next step is to balance them. So the difference between step 1 and step 2 is we have balanced them for anything other than oxygen and hydrogen. So notice that with regard to this half reaction on the left, we need to put a 2 in front of the chromium, right? And then over here on the right, we need to put a 3 in front of the I-. The next step is to fix our oxygens. So you can see that, and you guys have the answers in front of you, right? We fixed our oxygens on the left one. Since we have 7 oxygens here, we need to have 7 oxygens over here, again, on the product side. So the way we do that is introducing the whole water molecule. You're like, that feels a little overkill. Well, that's just what we do in this approach. Notice that we don't have any oxygens there. Since we introduced water on the left, we need to fix now our hydrogens. So in introducing 7 H2Os, we had, what, 14 hydrogens? So that's why we put 14 H+ over here. Again, we can do that because it's in acidic conditions. And we don't need to do anything with our right half reaction. So the next step is to balance it for charge. So this is how this looks. Let's see. Before I do that, I'm going to go backwards. Do you see what our charge is over here? So I'm going to put a brick wall here. This is actually step 4. I'm going to use step 4 to see what we're going to do for step 5. We have, of course, the charge on the reactant side, the charge on the product side. The charge on the reactant side, I got a -2, oops, go back. the other way, the other back. The charge on the reactant side, I have I'm going to have to do it above here. I have a -2 and I have a +14. Okay, so I'm like in what, +12? So I got +12 over here. And then over here, I have 2 times a +3. I have a +6. There's nothing there. So I have a +12 and a +6. So I need to make them both +6. I can do that if I add 6 electrons over here. That takes my +12 down to +6. That's exactly what I'm going to do. For this one, I have to go clear up to here, step 2, when we did something. So I'm going to put a brick wall here. Okay, and so I have 3 times -1, so I have -3. Over here, I have -1. So electrons are all we have to deal with, all we have an option to deal with regard to step 5. So can you see where if I put 2 electrons here, then they're going to be equal? That's exactly it. Okay, so we add 6 electrons over there to make our +6 on both sides. And we add 2 electrons over here to make it -3 on both sides. Okay. So the next step, what do we do? Oh yeah, the next step means, okay, we're getting ready to add them, but don't add them until you have the same number of electrons given up and taken in. Again, I'm not a math person, but I think my slides say we'll come up with the common multiple, the least common multiple. Okay, and it's 6. So I have 6 electrons that are absorbed over here, and I have only 2 electrons that are given up over here, so I can scale my 2 electrons up to 6. I do that by multiplying the stoichiometric coefficients by 3 on my each of my stoichiometric coefficients. Okay, so the 3 becomes a 9, the 1 becomes a 3, and the 2 becomes a 6. All right. Whew, ready for the Hail Mary. So adding the equations looks like this. Basically, I took this and put it right there. And I took this and put it right there on the product side. And this is what it looks like. Of course, right away, you're like, dude, those 6 electrons are so going away, right? And I'm trying to think, does it look like there's anything else? I don't think so. To me, it looks like 6 electrons are the only things that can go there. Okay. So we're going to switch it up, and it's going to be in basic solution. I didn't emphasize it, but the word alkaline also means basic, okay? So the thing about it is you're going to recognize these steps. You've done, what, 3 of these now? 1 and then 2 on your own. So you're going to recognize these first steps. So the thing about it, though, we have some kind of cleanup steps, okay? We're going to actually make sure instead of your H pluses that you ended up with, we're going to make sure that those have to be hydroxide ions because it's basic. So let's see what that looks like. It starts out, like I said, similarly. So if you, actually the first 5 steps are identical. What did you guys just do? You separated 2 half reactions. What did you do next? You balanced it for everything except oxygen. What did you do next? You balanced oxygen by adding water. Next, you balanced your hydrogens by adding H+. I know it's not an acidic solution, but you pretend like it is to start out with. The next thing that you did was to balance it by charge by adding electrons. At that point, you kind of deviate. Okay, you don't make the electrons equal out for both. You wait, okay? The next step is different. The next step is to say, okay, it's not in acidic solution, it's in basic solution. So for each of your H+, you're going to add the hydroxide ion to both sides of the equation. It's just like math. You can do that as long as you add it to both sides. So you're going to, you know what's going to happen. When you add hydroxide where there's H+, those are going to combine to make water. And then you're going to be left with extra hydroxides over here. So that's how you turn it basic. Okay. Yep. So step number 7 is to go ahead and clean it up after you added hydroxide. Go ahead and make your H pluses and your OH minuses where they're on the same side of the reaction arrow, combine to form water, and then you're going to go ahead and clean up your water because you might have water everywhere. So you're going to go ahead and where you have water on both sides of the reaction arrow, you're going to go ahead and whichever side has more, you're going to have some there, and it kind of cancels out. Kind of combining terms is what that's called, I guess. At that point, you're back to something you've done before because you went ahead and you made it equal for charge for in the half reaction, and now you're going to find that lowest common multiple, I guess it is, so that you're going to look at both half reactions and make sure that whatever electrons are given up are going to be consumed over here or whatever. So you're going to scale up what you need to, okay? And then you're ready to add them. That's my Hail Mary step. This is, Hail Mary to me is like if you're using Hess's law, you know, manipulating equations, you're like, I hope it makes the reaction of interest. So of course your electrons will go away, and you should be left only with the hydroxide ions, of course no H pluses, and verify your work. So let's do one together. And you're all kind of clustered back there. So we're going to start with Olivia and kind of go around. Well, you guys have done enough of this, okay? We're fine. If you break it down into two half reactions, okay, it's going to look like this. Where to me, so of course H2O2, does anybody know what that chemical is? Use it for sanitizing wounds. Hydrogen peroxide, it can hurt like heck, right? One of the things that we said, except you guys told me oxygen is -2, oxygen's -2, unless it's in its uncombined element form. But unless it's a peroxide linkage, then what is it? It's not -2, it's a -1, yep. So already right there you have oxygen going from a -1 to a -2, which is what, reduction again? Over here we have chromium going from a +3 to, what's this one? I'm asking you because I don't know. See, -8. I'm like in a +6. From chromium +3 to a, come on, you guys just did all
I
these.
thought you were asking like the name of it.
No, not the name, but what's oxidation state for chromium over here? Sorry, wasn't very clear. +6. Yeah, that's what I'm liking to. So anyway, I said we weren't gonna do it, but we did it. So we need to balance them for everything except oxygen. Nothing needs to be balanced over there. Over here we have nothing else. Like, dude, we just need to fix our oxygens. Again, we fix our oxygens by adding water, so it feels kind of silly. But like over here, to fix it for our oxygens, we have 2 oxygens here. We only have 1 oxygen here, so we need to add another water molecule. Isn't that fun? And then over here, on the product, or excuse me, on the other half reaction, looks like we have 3 oxygens and 4 oxygens. We need to fix it, add 1 more oxygen there. And then the next step is we fix our hydrogens. We can do that. We do that assuming it's in acidic conditions. So we introduced 2 hydrogens by adding 1 water molecule, so we need to add 2 H pluses over there. Over here, we need to add 5 H pluses because we introduced 1 water molecule, which gave us 2 hydrogens, but we already had 3 hydrogens as part of our chromium hydroxide. So 5 H pluses, I'm liking it. Okay, is number 5 the same? Okay, number 5 is the same, and then we're going to start to deviate. So now we got to look at both sides and recognize that we need to go ahead and introduce 2 electrons on the reactant side over here to make it, actually base looks like both neutral charge on either side. And here we need to introduce 3 electrons to make it, what, +2 on either side. Now this is different. So now I said you got to go back and clean up your H pluses. What that's to say is wherever you have an H plus, forever how many you have, introduce hydroxide ions. So that means for the first half reaction, we're going to have to introduce 2 hydroxide ions on either side of the reaction arrow. And in the other half reaction, introduce 5 hydroxide ions. Of course, those hydroxide ions combine to form water. And so this step kind of cleans that up. And it looks like I have step 7A and 7B. 7B goes ahead and says, let's get rid of the water as we can. So we have 2 waters over here and 2 waters over there. They go away. And over here we have nothing to combine over here. Okay. I guess we did. We have 5 waters and 1 water, makes 4 waters on the product side. And we're getting close. Now we recognize we have the whole 2 and 3 sort of thing. So the lowest common multiple is 6. So in this case, it's pretty exciting. We need to scale up both half reactions. Okay, so we multiply the one on the left through by a factor of 3 and the one on the right through by a factor of 2. Bringing up their stoichiometric coefficients, that gives us 6 electrons and 6 electrons. I love redox reactions. So then we're ready to combine them, and of course our electrons will cancel, along with hopefully probably something else. So electrons cancel, and what else cancels? Actually, hydroxides, we have 10 and 6, so it looks like the reactant side wins out with 4. And this is our balanced equation. I'm going to go ahead and write the 2 that I want you to do on the bottom here, because this is easier to write on, easier to read. It's not a race or anything, it's only 1 o'clock. But once you guys have pulled yourselves through these and they look good, then that's it for today's Latin, unless you have any questions. Before I go on or whatever, these are, if you want to jot this down, Mike, these are the same deal as I had before, where these are in basic solution, and you can earn 5 points for each of them that you do, and there's a C and D, so if you want to earn a total of 20, you can do that. And they're fun. Okay, so they're in basic solution. So up here are the 2 I want you to work. They look like this. The ClO -1. What's the name of that polyatomic ion? Hypochlorite. Okay, AQ reacts with CrO2 -1 AQ to form Cl minus AQ plus CrO4 2 minus AQ. That's a 4 right there. And then the second one I want you to do is NO2 -1 AQ reacts with solid aluminum, so ALS, to form NH3G gas plus AlO2 -1 AQ. Okay, so do those 2 in basic solution.